Hey there, it's Shannon Math Chick Myers. Today we're looking at the definition of the Laplace transform. This is from section 7.1 of the ZIL Intro to Differential Equations text. So in calculus, we learned that differentiation and integration are transforms. These operations transform a function into another function. So if you have something along the lines of, I don't know, your function is cosine of x. When you differentiate cosine at x with respect to x, we get negative sine at x, a whole new function with its own graph. And if we take a look at the integral of cosine at x with respect to x, we would get positive sine at x plus some constant of integration. So a whole family of functions for that one. These two transforms have the linearity property that the transform of a linear combination of functions is a linear combination of the transforms. So if you have the derivative with respect to x of some alpha times f at x plus beta times some g at x, that would equal to, using the constant multiple rule and the derivative of a sum is the sum of the derivatives, we would have alpha times d dx of f at x plus beta times d dx at g at x. And sorry, these would then be alpha times f prime at x plus beta times g prime at x. Groovy? And now, if you look at the integral of alpha times f at x plus beta times g at x, all with respect to x, we would have alpha times the integral of f at x dx plus beta times the integral of g at x with respect to x. All right. And where alpha and beta are constants, and provided that each derivative and integral exists. For this section, we check out a special type of integral transform called the Laplace transform. The Laplace transform has the linearity property, sorry about the dogs, and many other cool properties that make it useful in solving linear initial value problems. The integral transform. So if f at x and y is a function in two variables, then a definite integral of f with respect to one of the variables leads to a function of the other variable. An integral such as the integral from a to b of k at s and t times f at t dt transforms a function f of the variable t into a function capital F of the variable s. We are interested in an integral transform where the interval of integration is the unbounded interval from 0 inclusive to infinity non-inclusive. If f at t is defined for t greater than or equal to 0, then the improper integral, the integral from 0 to infinity of capital K at s and t times f at t dt, is defined as a limit. So our integral from 0 to infinity of K at s and t times f at t dt would be equal to the limit as b approaches infinity of the integral from 0 to b of K at s and t times f at t dt. If the limit exists, we say that the integral exists or is convergent. If it does not exist, the integral does not exist and is divergent. In general, the limit will exist for only certain values of s. We go forward assuming s is a real variable. The function k at s and t is called the kernel of the transform. If we choose k at s and t to be equal to e to the negative s times t as the kernel, we end up with an important integral transform. So first definition, 7.1.1, the Laplace transform. Let f be a function defined for t greater than or equal to 0. Then the integral L at f at t, this is the transform, equal to the integral from 0 to infinity of e to the negative st times f at t dt is said to be the Laplace transform of f, provided that the integral converges. Note, a lowercase letter denotes the function being transformed, and the corresponding capital letter denotes its Laplace transform. So, for example, L at f at t equals capital F at s, L at g at t equals capital G at s, and if you had L at y at t, you would get capital Y at, s. All right, example 1, please evaluate the following using this improper integral. So basically, this improper integral is finding the Laplace transform using the definition. We're going to learn some kind of shortcut rules in a theorem soon. But let's do it the hard way first. Fun, fun. So here we go. L at 2 means that f at t equals 2. So we're going to look at the integral from 0 to infinity of e to the negative st times 2 dt. Well, that is equal to the limit as b approaches infinity, the integral from 0 to b. We can take that 2 out of the integral, actually out of the limit, we'll do that soon. And then we would have e to the negative st dt. Now we're treating s as a constant, so it would be negative s would be the coefficient to the t. So I'll divide by that, and we'll end up with 2 times the limit as b approaches infinity of e to the negative s over t over negative s. And that's evaluated from t equals 0 to t equals b. And then continuing, we will have, this will be equal to negative 2 over s. I can bring that to the outside. And then I will have the limit as b approaches infinity of e to the negative s times b minus e to the negative s times 0. So that's going to give us negative 2 over s. So since we have a negative in front of that exponent in the exponential function, and we're taking it to infinity, just this first one, and s is given to be positive, that's going to be 0. And then the second one is just 1, and the limit of a constant is the constant, right? So we'll have 0 minus 1, and so that's going to give us positive 2 over s. And we're all done. Cool, cool? All right. Now let's take a look at L at t. So L at t will equal to the integral from 0 to infinity of e to the negative st times t dt. So that will be the limit as b approaches infinity of the integral from 0 to b of t e to the negative st with respect to t. So this one, we're going to need integration by parts. So over here, I'll just do it on the side. The indefinite integral, t e to the negative st dt. I'm going to let u equal to t. So du is dt. And then we'll have dv is equal to e to the negative st dt. So v is going to be negative e to the st over s. All right. So this will be equal to u times v. So putting it all together, we will have negative t e to the negative st over s minus the integral of v du. So let's see, we can go ahead, minus is plus. We can factor out that 1 over s, and then the integral, we'll have the integral of e to the negative st dt. So we will get the integral of t e to the negative st dt is negative t e to the negative st over s plus 1 over s times e to the negative st over negative s. Groovy? And so we'll have t e to the negative st dt. That integral will be equal to, let's see, we'll have, both of them have an e to the negative st, and they're both negative. So I'm going to factor out an e to the negative st, and then we'll have left over t over s plus 1 over s squared. Groovy? Okay, so putting it back over here, this will be equal to the limit as b approaches infinity of. So we'll plug in what we found, and that was negative e to the negative st times t over s plus 1 over, that's an s squared. And that's going to be evaluated from 0 to b. So we will get the limit as b approaches infinity of, we'll have negative e to the negative sb times b over s plus 1 over s squared and then minus is plus, and we'll get e to the negative s times 0 times 0 over s plus 1 over s squared. All right, and so this will be equal to, so we only need to worry about the limit for that first part, right? So I'm going to rewrite this just a little bit. We'll probably need to use L'Hopital's rule. So I'm going to multiply that through and we'll have negative b over se to the sb plus 1 over s squared, and actually that'll be minus because the sign on the e to the s times b. And that's the only term where we need to worry about the limit, because this next one, so that will be on its own, doesn't have any b's in it. And so e to the 0 is 1, and so we're going to end up getting plus 1 over s squared, because the limit of a constant is the constant, right? All right, so let's take a look. The first one, do you see that we're going to get infinity over infinity? So this, the first term right here. So here, this is going to be equivalent to the limit as b approaches infinity of the derivative with respect to b of numerator and denominator. So we'll get a 1, and then we'll end up getting s squared e to the sb, and it's with respect to b. Yes, so we're good there. And then, so I've applied L'Hopital's rule, and then minus the limit as b approaches infinity of 1 over s squared e to the sb. And then I have my plus 1 over s squared hanging out. So this in turn is going to now, do you see each of these will 0, right? So we'll end up getting negative 0 minus 0 plus 1 over s squared. So at the end of the day, 1 over s squared is our Laplace transform. Groovy? All right, so next up, we're looking at using the definition to find the Laplace transform of this guy. So lots of integration by parts stuff. Aren't you happy? All right, so this will be the integral from 0 to infinity of e to the negative st times cosine at 3t with respect to t. So again, we will definitely need to do our integration by parts, and it's a little bit of a long one. So we'll just go ahead over here and start our integration by parts. So we're looking at that. We'll just work with the indefinite integral of e to the negative st times cosine at 3t dt. So for the first part, u1, because you need to do these twice and equate like integrals. So u1 will be equal to e to the negative st, du1 will be negative se to the negative st. dv1 will be equal to 1/3, or no, I'm got to put it regular first, cosine 3t dt. And then v1 will be 1/3, and it'll have a negative, and then sine, no, we're integrating, sorry. And then when we integrate both sides, we'll get v1 is equal to 1/3 sine at 3t. And so plugging that in, we get u times v, u1 times v1. So I'm going to mix it on up. So we'll get 1/3 e to the negative st times sine at 3t. And then minus the integral of v du. But we'll have minus a minus to make it plus. And then we'll bring the 1/3 on the outside. And actually, we can also bring the s from du1 to the outside. And then what we'll have left is the integral of e to the negative st times sine at 3t dt. All right, so I'm going to keep rewriting this first integral because otherwise it's easy to forget that you have to combine like integrals. So we're going to have all of this stuff, right? So we have our 1/3 e to the negative st times sine at 3t plus s over 3. Now we got to do our second sub. So u2 is going to be the same, e to the negative st, and du2 will be negative se to the negative st. dv2 is going to now be sine at 3t, and v2 will be negative 1/3 cosine at 3t. And that's what we're going for, because we're going to be able to combine like integrals soon. So this s over 3 portion is multiplied to all this other second portion of your integration by parts. So just so that you're keeping track, no. Okay, so we will have our u2 times v2 is going to be negative 1/3 e to the negative st times cosine 3t. Again, we'll have that minus a minus situation. So be careful here. We're putting in the integral, you're subtracting the integral of v2 du2. So there's going to be 3 negatives. So we're going to end up with a negative s over 3 times the integral of e to the negative st times cosine at 3t dt. And then we're making progress. We'll have e to the negative st times cosine at 3t dt equals 1/3 e to the negative st times sine at 3t minus s over 9 e to the negative st times cosine at 3t minus s squared over 9 times the integral of e to the negative st cosine at 3t dt. Oops. And that was just from distributing. Now we need to combine like integrals. So these guys are like integrals. The one on the left has a coefficient of 1. The one on the right has a coefficient of negative s squared over 9. So I'm going to add the coefficients and then times the integral of e to the negative st times cosine at 3t dt will equal to, so I can, let's see, if I factor out e to the negative st over 9, I will have 3 sine at 3t and then minus s cosine at 3t. Cool so far? All right, almost there. And now I need to, I'm going to write this as 9 plus s squared over 9 times the integral of e to the negative st times cosine at 3t dt is equal to e to the negative st over 9 times 3 sine at 3t minus s cosine at 3t. So when I invert and multiply to isolate this integral, I'll have 9 over s squared plus 9 times e to the negative st over 9 times 3 sine at 3t minus s cosine at 3t. So those 9's divide out, and I will have the integral of e to the negative st times cosine at 3t dt equals to 1 over s squared plus 9 times e to the negative st times 3 sine at 3t minus s cosine at 3t. Groovy? Okay, so remember that we were dealing with the Laplace transform. So the Laplace transform of cosine at 3t is equal to the integral from 0 to infinity of e to the negative st times cosine at 3t dt. But that will be the limit as b approaches infinity of the integral from 0 to b of e to the negative st times cosine at 3t dt. And then we will have the limit as b approaches infinity of, we have our result, I'll write it in purple, and our result was 1 over s squared plus 9 times e to the negative st times 3 sine at 3t minus s times cosine at 3t. And all of that is going to go from 0 to b. So I'm going to take out this 1 over s squared plus 9 because that's not going to, that doesn't have any b's in there, and or t's where the b's will go. So we will have e to the negative sb times 3 times sine at 3b minus s times cosine at 3b. That's our upper limit of integration. Minus e to the negative s times 0 times 3 times sine at 3 times 0 minus s times cosine at 3 times 0. So that's going to be 1 over s squared plus 9. And my bad, I forgot my limit notation here, bad teacher, times the limit as b approaches infinity of all this. So when we send b to infinity, do you see that e to the negative infinity basically zeroes out, right? Because you'd be tending towards infinity in the denominator. So we're going to have a 0 times, now the sine function and the cosine function are capped, right? At their output is negative 1 to 1. And so no matter what happens with b, they'll just be capped. So we can just call the whole thing 0. Minus, notice that the second term doesn't have any limits, okay? So the limit of a constant is the constant. So e to the 0 is 1. Sine at 0 is 0. Cosine at 0 is 1. So we'll end up with minus 1 times 0 minus s times 1, which is s. And so at the end of the day, we will get s over s squared plus 9. Pretty cool, huh? All right. Well, it turns out that L is a linear transform. So for a linear combination of functions, the integral from 0 to infinity of e to the negative st times alpha times f at t plus beta times g at t with respect to t will be equal to alpha times the integral from 0 to infinity of f at t dt plus beta times the integral from 0 to infinity of g at t dt. Whenever both integrals converge for s greater than c. The c is going to come into play soon, so stay tuned. Following what the author said, and it's kind of early. All right, so it follows that L at alpha times f at t plus beta times g at t will be alpha times L at f at t plus beta times L at g at t, which in turn is equal to alpha times capital F at s plus beta times capital G at s. All right, so we're going to use our results from example 1 to illustrate the linearity of the Laplace transform. So L at the sum of functions, sum and difference of functions, is going to be equal to L at 2 plus 7 times L at t minus 4 times L at cosine times at 3t. And we found all of those. Remember that L at 2, way back when, was 2 over s. L at t was 1 over s squared. And then we got s over s squared plus 9 for the last one. So we're going to get 2 over s plus 7 times 1 over s squared minus 4 times s over s squared plus 9. So we'll get 2 over s plus 7 over s squared minus 4s over s squared plus 9. Groovy? All right, so theorem 7.1.1. Transforms of some basic functions. So, sorry, that's a little light. Hang on. So L at 1 is equal to 1 over s. L at t to the n is equal to n factorial over s raised to the n plus 1. And that's for n equal to 1, 2, 3, ... L at e to the at is equal to 1 over s minus a. L at sine at kt is equal to k over s squared plus k squared. And then we found this one, the transform, Laplace transform of cosine at kt, remember rk was 3, is equal to s over s squared plus k squared. And then, again, you may not have looked at the hyperbolic sine and cosine, but we might as well check them out. No need for you to be deprived. So the Laplace transform of the hyperbolic sine at kt is going to equal to k at s squared minus k squared. And the Laplace transform of the hyperbolic sine at kt will equal to s over s squared minus k squared. Groovy? All right. So now, sufficient conditions for existence of the Laplace transform at f at t. The integral that defines the Laplace transform does not have to converge. Sufficient conditions guaranteeing the existence of L at f at t are that f be piecewise continuous on 0 to infinity, where 0 is included, and of course infinity is not, and that f be of exponential order for t greater than some capital T. Recall that a function f is piecewise continuous on 0 to infinity if in any interval from 0 less than or equal to a less than or equal to t, which is less than or equal to b, there are at most a finite number of points t sub k where t sub k minus 1 is less than t sub k for k equal to 1, 2, ... down to n, at which f has finite discontinuities and is continuous on each open interval from t sub k minus 1 to t sub k. All right, what does that all mean? Basically, what you have going on you've got t, and then you've got some f at t is the vertical axis. And then let's say that this is A and this is B. And in between, sorry, this is kind of crooked, isn't it? Okay. And then in between, you've got some T1, some T2, some T3, and there's discontinuities. So in this example, I've got some jump discontinuities. So you're starting at 0, and let's say you're going down all the way to there, that discontinuity, and then you've got to jump up, and then let's say it goes up here, and then down to B. And keeps going. Cool. So what happens is you've got some jumps in there, but there's just a finite number of these jump discontinuities. All right, so a function, the definition 7.1.2 of exponential order, a function f is said to be of exponential order if there exists constants c, this is where that c will come into play, m greater than 0 and capital T greater than 0, such that the absolute value of f at t is less than or equal to m times e to the ct for all t greater than t, capital T. Note, if f is an increasing function, then the condition absolute f at t less than or equal to me to the ct, t greater than t, simply states that the graph of f on the interval from t to infinity non-inclusive does not grow faster than the graph of the exponential function me to the ct, where c is a positive constant. So what you would have is something along these lines. So you have your t, your f at t. Now, this, I'll do it in this color here. No, I'll do it here, a different color. So you've got, you know, some m e to the ct, c greater than 0 is in this kind of purpley or pinkish. And then here, let's say you've got f at t. So where they cross right here would be your capital T. So notice as t is greater than capital T, you've got your f at t is less than me to the ct. Cool, cool? All right, so a positive integral power of t is always of exponential order, since for c greater than 0, absolute t to the n is less than or equal to me to the ct, or isolating m, you would have absolute t to the n over e to the ct is less than or equal to m. For t greater than capital T is equivalent to showing that the limit as t approaches infinity of t to the n over e to the ct is finite for n equal to 1, 2, 3, ... The result follows from n applications of L'Hopital's rule, which we're not going to do today. Below are a few graphs of functions that are of exponential order. So if we let m equal to 1 and c equal to 1, then me to the ct will just equal to e to the t. Cool? So let's look at the graphs that we did, or the linear transformations that we did already. So they all had, we'll compare them all to just e to the t. Okay, so our different f of t's were, we had, remember, f at t is 2. We had found that Laplace transform of 2. So here, that would go through here, something like that. And this was for f at t being equal to 2. We also had an f at t equal to t, right? So that would be something like this. And then we had an f at t was equal to cosine at 3t. So that would start up here at 0, 1. And then go something like this. So you can see all of these that we had done. So our f at t equal to cosine 3t were all of exponential order. Cool, cool? All right. Next up, almost there, making some progress. Theorem 7.1.2, sufficient conditions for existence. If f is piecewise continuous on 0 inclusive to infinity and of exponential order, then L at f at t exists for s greater than some c. So we're going to use definition 7.1.1, the hard way, to find L at f at t. This is a piecewise function. So L of f at t will equal to the integral from 0 to infinity of e to the negative st times f at t dt, just like we've been working with. But that in turn will be equal to the integral from 0 to 1 of e to the negative st times 2t plus 1 dt plus the integral from 1 to infinity of e to the negative st times 0 dt. Well, fortunately, that second integral is just going to zero out. And so we will have, we're going to work with integration by parts. I'll just do it down here a little ways. And I'm going to let u equal to that whole 2t plus 1. So du will be 2 dt. dv will be e to the negative st dt. And v is negative 1 over s e to the negative st. So the integral of e to the negative st times 2t plus 1, that quantity times dt, will be u times v. So negative 2t plus 1 over s times e to the negative st, and then minus the integral of v du. So there's a negative for the v, so minus a minus is plus. And then we'll have 2 over s we can bring out. And then we have the integral of e to the negative st dt. And so that's going to give us negative 2t plus 1 over s e to the negative st plus, actually it'll be a minus 2 over s squared times e to the negative st. So I'm going to rewrite it as negative e to the negative st times 2t plus 1 over s plus 2 over s squared. And then we'll bring that back up. So here, that's going to be the integral from, actually we already have that. That's going to be negative e to the negative st times 2t plus 1 over s plus 2 over s squared. And then that's going to be evaluated from 0 to 1. And the other integral is just 0. So that's nice. And so continuing the work on this one, we will have negative e to the negative s times 1 times 2 times 1 plus 1 over s plus 2 over s squared. Minus a minus is plus. We'll have e to the negative s times 0. And then 2 times 0 plus 1 over s plus 2 over s squared. And then that's going to give us negative e to the negative s times 3 over s plus 2 over s squared plus 1 times 1 over s plus 2 over s squared. So if I want to group my s and my s squared terms together, I would then get 1 over s times 1 minus 3e to the negative s, and then plus 2 over s squared, and then we'll have 1 minus e to the negative s. And we're all done. This was just all our work on our integration by parts. All right, cool. Now, behavior, theorem 7.1.3, behavior of the linear transformation as s approaches infinity. So, if f is piecewise continuous on 0 inclusive to infinity non-inclusive and of exponential order, and capital F at s is equal to the linear or the Laplace transform of f at t, then it turns out that the limit as s approaches infinity of that resulting Laplace transformation is 0. So example 4, we're going to use the theorem, so the quick stuff, to find L at f at t. All right. So L at f at t is going to equal to L at, actually, negative 4 times L at t squared, so I'm using the linearity property of it, plus 16 times L at t, and then plus 9 times L at 1. And then using our list here, right, L at t to the n is n factorial over s to the n plus 1. So our n is 2. So we'll have 2 factorial over s to the 2 plus 1. And then, remember, we found that transform for t. So this one will be plus 16 times 1 over s squared. And then plus 9 times 1 over s. So this was the output for this guy. And that's going to give us 2 factorials, just 2. So we'll have negative 8 over s cubed plus 16 over s squared plus 9 over s. And we're done. Isn't that groovy? All right. And now this one's a little trickier, right? We got to use a trig identity because we don't have anything in our list right here for cosine squared at something, right? We have cosine kt, which was s over s squared plus k squared. So let's work with that. In order to integrate cosine squared at t, you would have had to learn that this is equivalent to 1 plus cosine 2t over 2. So we can rewrite it as 1/2 plus 1/2 times cosine at 2t. So our k would be 2 for that cosine term. So L at f at t will be equal to L. I'm going to write it as 1/2 times L at 1, so I can match it up perfectly, plus 1/2 times L at cosine 2t. So that's going to give us 1/2 times 1 over s plus 1/2 times, so it's s over s squared plus k squared. So we'll have s over s squared plus 2 squared. So then that gives us 1 over 2s plus s over 2 times, I'll just write it as one happy deal, s over 2 times s squared plus 4. And we're all set. And I think that's it. Yep, we're all done with this video. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, hit that like button and subscribe. Bye.